and welcome to the session of Power Electronics. Today we are going to discuss a topic called as phase control converters. Now we know there are many of applications of AC are available in commercial market. Few of them are phase control converters, inverters, choppers, cycloconverters, AC voltage regulator and many more. For the sessions of power electronics, we are going to discuss these applications further. So we are going to start today. We are going to start with the first application, that is phase control converter. So let's see what are its content. So we are going to get introduced with these converters. Then we are going to classify these converters. Then we are going to discuss the working of single phase half wave control converter with resistive load. And then we are going to derive the DC voltage for it. So let's start with what are the phase control converter. What is a phase control converter? Phase control converters are nothing but rectifiers. Rectification is the process of conversion of AC voltage or current into a DC voltage or current. Or we can best describe it as it is a process of conversion of bidirectional current or voltage into an unidirectional one. So the rectifiers basically uses a switching elements like semiconductor diodes, power transistor, power MOSFET, IGBT, SCR, and many of them. So for this, as we are discussing the power electronics session, we are going to learn all the circuit by using a SCR, but any of these components can be used. Now on the basis of switching elements, these rectifiers or converters are classified into three broad categories as uncontrolled converters, fully controlled converters and half controlled converter. Now why they are named as like this, let's compare them. So uncontrolled converters basically uses semiconductor diode as their switching element, whereas fully controlled converter uses SCR as their switching element, whereas half control uses combination of diode and SCR as their switching element. Because of use of diode, actually the challenge with this rectifier circuit is that their output voltages only depends on value of supply voltage. If you remember the value of VDC for half wave rectifier, it is Vm by pi, which is almost 0.32 times of Vm. Whereas if you go for full wave rectifiers, it is almost twice Vm by pi, which is almost around 0.64 times of Vm. So these equations tells us that VDC is directly proportional to the value of Vm. Means as the supply voltage varies, the value of output voltage will vary. Or if the supply voltage is constant, the output voltage will be constant. This means that the output voltage depends only on the supply. It is not depend on any of the switching element. That's why we are saying that the output voltage is constant. Whereas if you go for fully controlled converter, the output depends on amplitude of the supply voltage as well as firing angle of SCR. So for fully controlled half controlled half controlled converters or rectifiers, they are using SCR as their switching element. So you can adjust the firing angle. If you remember, SCR have a capability to adjust the firing angle so that we can turn on the SCR at any particular desired point of your sinusoidal waveform, and according to that, the output voltage can get varied. So this is the best part of addition of SCR, that gives us a control feature, and we can provide a variable output voltage. So same AC to DC converter which was constant with the diode now can be used as a variable with the AC by addition of SCR. Now if we obviously on the basis of cost, if we compare, obviously the uncontrolled converter will be quite cheaper compared to the fully controlled and half control. Half control, as they are using combination of diode and SCR, obviously there will be less costly. Let's further classify these uncontrolled, fully controlled and half controlled rectifiers on the basis of their circuits available exactly. So rectifiers, they are further classified on the basis of supplies, single phase and three phase. Single phase further classified into two types, as we traditionally know this particular classification: half wave rectifiers and full wave rectifiers, or you can say converters. Full wave converters further classified into two types: center tap and bridge. Now similarly, if we go for three phase converters or rectifiers are also known as pulse converters. In industrial application, mini pulses to 3 pulses, 6 pulse, 12 pulse, 24 pulse, like that, these pulses can be used to minimize the ripple factor. So that's why very much three phase converters are very much known as pulse converters. Now there are two types: half wave and full wave only. Now if we go for fully controlled converters, it is just replacement of a diode with a SCR. So the circuit remains the same for uncontrolled and fully controlled. As we can see, the same classification is available in uncontrolled as well as in fully controlled converters. Now if we go for half control converters, as we know, half control is a combination of diode and SCR. So obviously there will not be any category available with the half wave circuits. There will be only category available with the full waves, obviously. That's why there are only two classifications with the single phase: symmetrical, asymmetrical. Same will be available with three phase: symmetrical and asymmetrical. We will discuss these sessions in detail with as we go for the next sessions. So today our main topic of discussions will be the rectifier, fully controlled rectifier, or rather we are going to start with half wave single phase half wave fully controlled rectifier. Now these circuits circuits can be discussed with different types of loads. Let's see what are the loads that we are going to discuss. As we are going for industrial application, obviously the loads can be resistive, can be inductive, and there is a problem with the inductive loads. That to overcome these problems, we are going to use the loads with freewheeling diode or flywheel diode. We'll discuss in details. Till this point, it is not necessary. So let's start with the main part of discussion for this particular session is a single phase half wave control converter with obviously the resistive load. So let's look at the circuit for this. Now, as we can clearly see from the circuit diagram, the circuit is similar to the half wave rectifier. The only change is that the diode is replaced with the SCR, the same circuit. So, if we like to describe about 230 volt 50 Hz AC supplies connected through a step down transformer to a half wave control converter circuit, which is connected in series with your load, obviously. So, one of the key thing which we like to mention over here, the SCR used in this circuit is having forward breakdown voltage value very higher than maximum value of the supply voltage. Now we are going to divide this working into parts. One will be for the positive half cycle, then we are going for the negative half cycle. So let's start with the first positive half cycle. Now in positive half cycle, let's say 230 volt 50 Hz AC supply is applied, and if first positive half cycle is available. So if positive half cycle is available, quite naturally P1 becomes positive, P2 becomes negative. This induces voltage drop across secondary, that makes S1 becomes positive, S2 becomes negative. Now because of this, the SCR will be in forward bias condition. So obviously because of this polarity, SCR will be in forward bias condition, but it remains in off condition because we have selected that the forward breakover is very higher than maximum value of peak value of secondary. Now let's say consider any instant, let's say any instant alpha. As soon as a gate pulse is applied, it forces the SCR to goes in on condition. As soon as SCR goes in on condition, it produces a load current with a path S1 positive through T1 through RL through S2 negative, through which it will be grounded. As soon as load current is established, it helps to develop a load voltage, and because of that load, obviously we will observe a load voltage. Now as the load is resistive, obviously the load voltage, load current and the supply voltage will be in phase. The load voltage, load current and will be in phase with the supply voltage. That is the key thing which we like to mention over here. Now to sum up with this mode, we suggested that the SCR goes in on condition, we got a maximum load voltage, obviously we got a maximum load current for this particular waveform. Now let's see what happens with the waveform. Now as we have applied the positive half cycle, at the instant alpha we have applied a gate pulse to the SCR. This allows the SCR to goes in on condition. As soon as SCR goes in on condition, obviously it will conduct. Now what happens, this SCR will conduct from the instant alpha to pi. Now what happens at the instant pi? At the instant pi, now what we observed that the supply voltage becomes 0. As soon as supply voltage reduces to 0, it reduces the current flowing to the SCR below holding current value. As soon as current flowing to the SCR decreases below holding current value, the SCR goes to off condition. As soon as SCR goes in off condition, the load current reduces to 0. As load current reduces to 0, load voltage will be 0. So at the instant pi, the supply voltage becomes 0. So the load current flowing through the SCR becomes 0 and load voltage becomes 0. So let's go for the working of next half cycle, that is a negative half cycle. Let's start with negative. Now in negative half cycle, now the let's see if 230 volt 50 Hz AC supply is applied, and if negative half cycle is available. So if negative half cycle is available, that makes P2 as positive, P1 as negative. This induces voltage drop across secondary, that makes S2 as positive, S1 as negative. Now because of that, it reverse biases the SCR. So obviously as SCR is in reverse bias condition, it remains in off condition. Now as SCR is in off condition, there will not be any current, load current or load voltage, no current will be established, no load voltage will be developed. Now even if we apply a gate pulse, still as SCR is in reverse bias condition, there will not be any production of current or voltage will be developed, load voltage will get developed. So to summarize this particular negative half cycle, we can say that SCR is in off condition, load voltage becomes 0, obviously the load current becomes 0. Now if we compare on the basis of waveform, let's understand this working on the waveform. So on the waveform, we can clearly see that negative half cycle is available. Now even if we apply a gate pulse at the instant pi plus alpha, still the SCR remains in off condition. So there is no production of current or load current that will be established. So during this particular negative half cycle, the load voltage, load current and SCR completely will be 0, or the SCR will be in off condition. Now let's start with output waveforms. So we are going to draw the supply voltage waveform, the gate voltage waveform, load voltage, load current, voltage across SCR and current flowing to the SCR. So let's start with the waveforms. As soon as sinusoidal wave, let's say we are consider drawing for the half cycle. So let's start with positive half cycle and let's try to understand the working on the basis of waveforms as well. So now let's start with the, as we know the first positive half cycle is applied. As positive half cycle is applied, the SCR is in forward bias condition, but as gate pulse is absent, SCR remains in off condition. So no load current, no load voltage, and SCR current will be completely zero. Now let's consider an instant that what we suggested alpha. We will apply a gate pulse. As soon as at the instant alpha a gate pulse is applied, it forces the SCR to goes in on condition. We know that as soon as SCR goes in on condition, it jumps to a lower impedance state or lower potential state. So we can clearly see that the SCR goes in on condition, it jumps to a lower impedance state. As SCR goes in on condition, it allows a load current to get established and load voltage to get developed. Now we mentioned with this stage of working that during a positive half cycle, as the load is resistive, the load current and load voltage will be in phase with the supply voltage, so they will replicate as the supply voltage. They will replicate the shape of the supply voltage waveform. Now, as we mentioned at the instant pi, so this process will continue till the instant pi. At the instant pi, the supply voltage will reduces to zero. So obviously it forces the SCR to goes in off condition. As SCR goes in off condition, the load current becomes zero, the load voltage becomes zero. So the same process that we discuss with the working. Now let's go for the negative half cycle. In negative half cycle, we mentioned that as soon as negative half cycle is applied, SCR is in reverse bias condition. So as SCR is in reverse bias condition, it remains in off condition. As SCR is in off condition, it maintains maximum. It acts as an open circuit, and when it is acting as open circuit, all the negative voltage will be developed across it. So we can clearly see from the waveform, all the negative voltage is available across SCR. Even if a gate pulse is applied at the instant pi plus alpha, still the SCR is in off condition. So no load current, no load voltage. Also the current flowing to the SCR becomes zero. So the same waveform, this same structures or same shape can be replicated for the next half. So this completes our positive and negative half cycle. Let's see how it goes for the next half cycle. So again, next half cycle will be positive after 2 pi. So again, positive half cycle will be available. SCR will be in forward bias condition, but it still is in off condition. So no load current, no load voltage. At the instant 2 pi plus alpha, as soon as gate pulse is applied, it forces the SCR to goes in on condition. Again, it jumps to a lower potential state, allowing a maximum current, load voltage, and because of that, current flows to the SCR as well. Again, the supply voltage will be in phase with the load current. Load current and load voltage will be in phase with the supply voltage. Now, during negative half cycle, SCR remains in off condition. So all voltage will be available across SCR, even application of after the gate pulse. So this is all about the output waveforms for this SCR. Now we are interested in calculating the DC voltage drop across it. So DC voltage across load can be calculated by using a load waveform. Now what is a DC voltage? DC is nothing but called as average. So average means we have to perform average of this particular waveform. This waveform should be average. So this average will be somewhere down the line over here, or somewhere somewhere down the line, somewhere down the over here. So we'll get a DC voltage around this particular line. So let's try to establish or try to generate a relation that gives us what will the value of VDC, right? So let's start with, now what we mentioned, VDC is called as average, and that can be calculated by a formula, area under one complete cycle divided by base. Now one complete cycle, a complete cycle starts from for a sinusoidal signal, a cycle starts from 0, ends on 2 pi. So as the signal is periodic after 2 pi, so obviously so my base becomes the starting the ending point of the waveform and starting point of the waveform. So the formula for the base will be maxima minus minima, so that becomes 2 pi minus 0. That's why it gives me the base as 2 pi. Now to calculate the area under one complete cycle, as it is an instantaneous sinusoidal signal, so we need to apply integration over this particular waveform. So let's see how we can apply the integration. So this is what is the load voltage waveform, where we like to calculate the DC or average voltage across this. So if I apply integration over the load, that will be integration over the limit from starting point to the ending point over the load voltage with respect to omega t. Now as we can observe from the load voltage waveform, there are three different values in from 0 to pi. So from 0 to alpha, the load voltage is 0, as we can see from the waveform as well. Again, from pi to 2 pi, we are having a load voltage, the value of load voltage is 0. And from alpha to phi, we are getting a voltage which is in phase with the supply voltage. So that is why we obtain the value of load voltage as Vm by, into sine of omega t in the interval alpha to pi. Now, as we are having three different values, we need to split the integration in three parts. So the integration will be split from 0 to alpha, alpha to pi, and pi to 2 pi. Now let's substitute the value of load voltage in each interval. So for this the value is 0. For this it is Vm sine of omega t. For this interval the value is 0. So as we can so let's see. Now we know that integration of 0 is 0. Again, integration over the limit pi to pi 0 is 0. Now, as we know, the integration is not integration is over the omega t. That's why Vm is constant. So we are taking Vm outside of the integration. So this Vm will be placed outside of integration. Now we know that. Let's apply the integration. Integration of sine of omega t is minus of cos of omega t. So let's put apply the integration. The integration of sine is minus cos of omega t over the limit alpha to pi. Now to solve it further and to apply the limits, to simplify the circuit, we'll take this minus sign out of this particular bracket so that it will simplify for the solve. It is not needed actually. If it is just for the simplification we are doing this, but actually it is not necessary to. We can keep the negative sign over there itself. Now let's apply the limit. Let's put the upper limit and lower limit. So that gives me upper limit minus lower limit. So area is equal to minus of Vm cos of upper limit minus cos of lower limit. Now the value of cos pi is minus 1. So cos pi, we have substitute the value of cos pi as minus 1. So cos alpha remains as it is. So we have a equation of minus of Vm minus of 1 minus of cos alpha. Now let's multiply minus sign into the bracket. That is what I mentioned. It is not necessary to take out the minus sign because this increases our additional step. So let's go further. So minus sign will get multiplied inside. So that gives me the area as finally Vm 1 plus cos alpha. So we obtain the area as well as base. So now what the VDC was. VDC is all about area divided by base. So area Vm 1 into 1 plus cos alpha divided by 2 pi. Now if you remember, we started with a rectifiers, and in fully controlled converters we mentioned that the output depends on two factors. One is amplitude of supply voltage as well as firing angle of SCR. So this clearly justifies what we started, where we have started, that output depends on, not only depends on the amplitude of the supply voltage, but also it is depends on the value of firing angle. Now this is what we obtained for the DC voltage of single phase half wave controlled converter with resistive load. Now if I go for different values of alpha, let's substitute the different angles for alpha. If I substitute 0, so obviously the value of cos 0 is cos 0 is 1. So that gives me 1 plus 1 2. So that becomes 2 Vm by 2 pi. That gives me the value of Vm by pi. So if you remember, it is the same formula of half wave rectifier. So it is the voltage of half wave rectifier. 1 by pi is 0.32. So that becomes 0.32 times of Vm. Now if I substitute the value of pi by 2, that is 90 degrees. So cos of pi by 2 is 0. So I will get a value of Vm by 2 pi. That is the half of half wave rectifier. Now if I go for the value of cos as pi, that is 180. So at the 180 degree, cos pi is minus 1, 1 minus 1 0. So that gives me the value of VDC as 0. So as you can observe that as the value of firing angle is varied from minimum value to the maximum value. So for the minimum value we will get the maximum voltage, whereas for the maximum value we are getting the minimum voltage. If you remember, as the firing angle of SCR increases, the value of VDC will decreases. That is what we have observed. So let's summarize this particular session. In this session we understand that we have classified the rectifiers on the basis of switching element. We have discussed the working of single phase half wave control converters with resistive load, try to plot the waveforms. Also we have derived the VDC, and one of the key things which we mentioned that the output depends on amplitude of the supply voltage as well as firing angle of SCR. So these are the contents I have taken from our textbook Power Electronics. These are the page numbers that are also mentioned. So myself Amit Naik, and thank you very much for watching this.